Okay, so I see on our help document we want some help converting radians to degrees. So let's do that. So the important thing is that pi radians is equal to 180 degrees, which is also equal to 1/2 rotation. So whatever unit you're in, you and whatever unit you're trying to get into, you create a fraction where you cancel the current units and you put on top the desired units. And if you have the correct coefficient on those units, then the top and bottom of the fraction are equal to each other. So that means the fraction equals 1. So multiplying by that fraction doesn't change the value of what you're looking at. So if I have something like 144 degrees and I want to convert that into radians, I know that pi radians is equal to 180 degrees. Since this fraction has equal numerator and denominator, fraction equals 1. Multiplying by 1 doesn't change the value, so multiplying my angle by this fraction only converts units. The degrees cancel out, the radians are left behind, and and it doesn't change the value, it just converts the degrees. So I have 144 pi over 180 radians. Looks like I can cancel a 4 from the top and bottom. So actually, I can probably cancel a 12 from the top and the bottom. So let's see. If I cancel a 12 from the top, I get 12 pi. On the bottom, I cancel 12 and I get 15. And I can cancel another 3 out of this. So I get 4 pi over 5 radians. This is the same angle as this. It says converting back and forth between these. So same thing. If I have maybe, let's say I have 7 pi over 12 radians. I still know that pi radians is equal to 180 degrees. So this time I'm going to multiply, but I need to cancel the radians, so I put those in the denominator. I want to end up in degrees, so I put that in the numerator. The radians cancel, the pi cancels. I get 7 times 180 degrees over 12. I can cancel a 6 from the top and the bottom. That gets me 7 times 30 over 2 degrees. And I can cancel a 2. That gives me 7 times 15 degrees, which is 70 plus 35 is 105 degrees. That is the same as that. So let's see. That I hope that that helps. Convert radian in degrees, 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 radians in degrees, radians in degrees. You put this into the spreadsheet lots of times. Okay, so more examples of using sine, cosine, and tangent in right triangle problems, like figuring out which side is opposite or adjacent to an angle. Okay, so let's down here. Go. And let's get a practice problem of this type. Okay. Okay, so I have here a triangle. This is a right angle. This side is length 7. Here's A and B are sides we don't know, and this angle here is marked as 30 degrees. So, since this is the marked angle, that means this side is the opposite. This corner is the 90-degree angle, so this is the hypotenuse. And this unknown side is the adjacent. Opposite, adjacent, and hypotenuse. So, when you have a right triangle, whatever angle you're looking at, because you're not going to look at the right angle, you already know it's a right angle. But whether you're looking at this angle or this angle, they will both connect to the hypotenuse. And that means that this angle has, this is the adjacent side, and the other side is the opposite side. And this angle as this side is the adjacent side. Adjacent just means the side that touches it. Adjacent means close to or touching. Opposite means across from. So, if I want to find A, for instance, I know that this is a 30-degree angle, and I also know that A is the adjacent. I know that 7 is the opposite. So I think about, well, what trig function uses the adjacent and the opposite? And I go, oh, well, tangent is going to be opposite over the adjacent. Or I might go cotangent adjacent over the opposite. Either way, it doesn't really matter. But then we're going to solve for A in our equations. 7 times the cotangent of 30 degrees, A. And cotangent of 30 degrees is one of our special angles. If you don't recall, and up with our special angle chart. Have angles 0, 30, 45, 60, 90, down low there, 0, 1/2, 1 over the square root of 2, root 3 over 2 and 1, minus 1, 3 over 1 over the square root of 2, half 0. It's going to be the sine over the. We see that at 30 degrees, cotangent is 7. For B is the hypotenuse. We still have 7 is. What trig functions have a hypotenuse? And that would be cosine set up cosecant of 30 degrees to hypotenuse 7. Cosecant is 1. So cosecant 0 is undefined, and cosecant is the and so we just. But we can look at 30. How we know we have side that's 7, side that's 17, side that's 14. Okay. Another one. Okay, so I have a tree, and this, yeah, that looks kind of tree-like. This angle is 57 degrees. The distance from the tree is 30 feet. I want to know how tall this tree is. Well, this is the angle we have marked, which means this is the hypotenuse, adjacent. This is the opposite. You say, well, what do we know that has an opposite and an adjacent in it? Tangent and cotangent. Tangent is going to be the opposite over the adjacent. Cotangent is the adjacent over the opposite. Since we're solving for the opposite, we don't want it in the denominator, so this is our preferred form. Let's plug everything in. Tangent of 7 degrees equals the opposite, which we don't know. Using 0 is a bad choice. It's just over a, which is 30. That means x equals tangent of 57 degrees times 30 feet. And now we pull out a calculator. Big calculator. Off. Deal with it being pretty large. Have 30. We probably, with this calculator, I think we have to type in the angle for, type in an angle of 7. And this should be degree. I get 46, 46 points. Now I do want to show you, like, this can be confusing. This button here says DEG for degrees. If I click on it, it says RAD for radians. I want to be careful because some calculators, what it says is the mode that it's in. So right now it's in degrees, and if you click on it, it will change to a different setting. But some calculators, it is telling you the setting that you will go into if you click the button. So in some calculators, it'll say degrees, and that means if I click here, I am now in degrees. And I see radians because if I click there, I am now in radians. But that's not how this calculator works. You need to know how your calculator works. Is it showing you the current mode or the mode that you will switch into if you hit the button? The way to check is to type in 90 and then type in sine. So I've typed in sine of 90 degrees and I've gotten 1. That's correct. Sine of 90 degrees is 1. If I type in the sine of 90 radians, I will not get 1. See, I type in sine of 90, but I'm in radian mode and I do not get 1. I do this check with every new calculator that I'm unfamiliar with. If I'm doing trigonometry, if I'm not doing trigonometry, it doesn't matter, you know. But if I'm going to be using a trig function on a calculator and I have not used this calculator before, I will type in sine of 90 to figure out, is it in degrees or is it in radians? And then I'll do my math appropriately. I just want you to be aware of that. Okay. So, we did 2 of those. I hope it's okay. Let's see. We have examples of using sine, cosine, tangent, and right triangle problems, like figuring out which side is opposite or adjacent to an angle. Hope that I solved that problem with these. I'd like more examples of using sine, cosine, tangent. I think that's what we're looking for here. More practice of real world problems and knowing how to set up the problems in order to find what they're asking for. Is the tree real world enough? Maybe, well, when we get to the general triangle chapter, like right now we're doing right triangle trigonometry, which is nice. It's nice to have a triangle that has a right angle in it. But when we get to just general trigonometry and don't necessarily have a right angle, we're adding together like compass. This might be like 45 northeast at 2 miles. Plus, maybe we get 120 degrees northwest for 3 miles. Maybe that will satisfy the itch for more real world problems. But with this problem here, we don't have a right angle. It's not true that compass directions will always. Most of the time, you're not using right triangles when you're doing compass map stuff. Will we be graphing complex trig equations? Depends what you mean by complex. So let's give an example of something that we might do and something that we won't. Okay, so something that we could do is maybe like y equals negative 2 tangent of, let's say, 1/2 x plus I over 3 pi over 4. Let's do pi over 4. Plus 1. Okay, this is something we might do. On the other hand, something like y equals sine x plus cosine x is something that we're not going to graph. Okay. It's a neat graph. You could plug it into Desmos, but doing graphs of trig functions that are added together or multiplied is not what we're going to worry about. You might see these graphs in problems, but you will not be expected to graph those types of questions. So let's do this one. Here are my steps. Number 1, find the offset. Offset is going to be that number when you're in this form. So my offset is up 1. I will do that. Next, I find the amplitude. It's going to be 2, and I'm going to have a reflection on my, so I'll have to pay attention. Go up 2, and we'll go down 2. y equals 1, and y equals -1, and y equals... The next step that I have is I want to find the offset, or sorry, the phase shift. And to do that, I will have to factor the coefficient of x off of the stuff that's inside the trig function. So this becomes my phase shift. It is pi over 2. And since I am adding, this would be pi over 2 to the left. If it were positive, it would be to the right. Or if I were subtracting, it would be to the right. But since I'm adding, it'll be to the left. Which might feel backwards, but it's the way it works, and you can check this by plugging in some points into the equation and seeing how it moves. So I want to go pi over 2 to the left. Let's call this pi over 2. I'll call this pi. So tangent starts on its center line. I'm going to put a dot on the center line. The fourth step is to find the wavelength, which is going to be this coefficient. We're going to set up a fraction where we have either pi or 2 pi on top, depending on which function we're in, over whatever that coefficient. And then you simplify the fraction. So we're going to count over 1, 2. Here's the end of the wavelength. Halfway between the two waves, or halfway between the two ends of a wave, we have an asymptote. Halfway between the asymptote and the node, we hit either the crest line or the trough. Normally, you hit this point on a tangent. You go up the crest line, but because of this reflection, we're going to hit the trough line instead. We go down like this, and halfway between the asymptote and the node, we will hit this crest line again up here because of the flip. That, and then we repeat this. So half a wavelength, half of pi is going to bring me up there and up to infinity at negative 1.5 pi. Here we are going to come down. So this is at pi over 2. This is at 5 pi over 2. This is at 3 pi over 2. This one is at pi. This one is at... Steps are find the offset, amplitude, find the phase shift, find the wavelength. Then we plot. Length of an arc and speed on a circular path. So with an arc, that's some portion of a circle. So if we know that the radius of our circle is like that radius, then we know the circumference equals 2 times pi times the radius, pi. Distance all the way around is 6 pi. If we want an arc that is, let's say, 120 degrees, then we say, well, all the way around is 6 pi, and we want the fraction that is 120 out of the 360. So that would mean what? 6 pi times 1/3 gives us 3 pi. So going 120 degrees gets us 2 pi circle. If I wanted to go, let's say 200 degrees, take 200 degrees out of the circle. And I could cancel. Let's see, 40 goes into pi over 3. That is how far this much of circle. Same thing works with radians, although there is some nice cancellation that happens if you use radians. Let's suppose I have a circle and I have a radius of 12. Now, I know that the circumference equals 2 times pi times the radius, but with radians, I'm just measuring how many radii I'm going around. So that means that all the way around is just 2 pi times 12. If I have a wedge that's maybe 5 pi over 6-ish, then I know that I'm going this far around the circle, and the radius is, each radian I travel, I'm traveling the length of the radius. That's the definition of a radius. It's one radius around the circle. So if my radius is 12, then 5 pi over 6 radians of arc is going to come out to be 5 pi over 6 times 12. Cancel a 6 and pi. So it's nice. Like, one of the reasons that radians are really nice is that for any arc that I'm measuring, if I know how many radians my angle is, and I know how big my radius is, it's always just the number of radians times the length of the radius. Which is not bad. How far is 4/5 4 pi over 5, 4 pi fifths radians. How far is 4 pi fifths radians if the radius is 10? Well, it's 4 pi over 5 times 10. And in whatever units you're measuring, in inches, feet, meters, whatever. Okay, keep going. Little confused on the homework. Do you want us to just submit multiple screenshots of our work answers? Yeah, that's how you would submit them. So you'll write out your homework and then you can scan them or take pictures and then upload. That works. Let's see. I think there may be issues with the due dates and quiz content. Exam 1 is over chapter 1 content, but quiz 2 says prep for exam 1. I will have to look into that for next semester. The exam covered the stuff from quiz 1 and quiz 2. So, let's see. More help with amplitude, wavelengths, and arc lengths. Okay. Worked with arc lengths. More help with amplitude, wavelengths, and radians. So, those are up. Yep. Okay. So I guess what we should do, we'll look at the wavelength is the distance from um, the distance on one of these trig functions that it takes until we get repetition. So we're at the peak of this curve here. We come down through this trough here and we come back up to the crest. This takes, on sine, takes 2 pi. This is the same thing for cosine and secant and cosecant. So let's draw each of these. So it takes, for each of these four, we have 2 pi as our wavelength. Pi, 2 pi, and for the other trig functions, our wavelength is going to be just pi. Distance from here to here. So this is why when we are finding the wavelengths for sine, cosine, secant, and cosecant, whatever the number is here, Vx, these will all give you a formula for the wavelength of pi over. But for tangent, let's use x. Well, cotangent wavelength is w pi over. So if you have sine of 2x, the wavelength will be 2 pi over 2, which equals pi. But if you have tangent of 2x, this gives you a wavelength of pi over 2. That 2 isn't there to cancel. So for the same coefficient on x, tangent and cotangent will have half the wavelength of the other four functions. Looking back at this, the amplitude is the distance from the midline up to the crest, or from the midline down to the trough. Crest, there's the trough. For sine and cosine, these values mean the top and bottom of their wave. For the other ones, it's a little weirder. So we have here the crest line hitting the bottom of this chunk of the wave at this point, and the trough line going through and hitting the top of this bump down here. Trough and crest. And the same thing. So if we have 2 sine of x that we're graphing, the distance from this line to this line is 2. If we have 3 cosecant of x, that means the distance from the axis to that line is 3. That line being that very bottom tip of the little stalactite parts of the graph. Like stalactites up here and stalagmites down. For tangent, it's a little different as well. The amplitude is the point that is halfway between the node and the asymptote by your amplitude. So have tangent of 2x. What that means is here's my node, here's my asymptote. Halfway between the node and the asymptote, we hit a height of y equals 2. 2 tangent. This is where the amplitude. So this point has a y-coordinate of 2 because of this 2 in front of the tangent. Like, I have to go. I'll talk to you later. Bye.